Imagine the universe not as a cold, static world, but as a vast, flexible fabric. When the most violent and energetic event in a cosmos occurred, like the explosive collapses of massive star or two black holes locked in a fatal cosmic dance, they don't just happen in a space; they alter it. This cataclysmic event generates invisible repulses in the very fabric of space-time. Traveling at the speed of light, they stretch and squeeze everything along their path. They are cosmic messengers, carrying us secrets about their violent origin and fundamental nature of gravity itself. We call them a gravitational waves. Now, a scientist had speculated about these waves since late 19th century, but it wasn't until 1916 that Albert Einstein formally predicted their existence through his general theory of relativity. Einstein shows us that gravity isn't just a mysterious pull, it's just a warping of space-time, and when massive objects accelerate quickly, they create a repulses much like dropping a stone or rock into a quiet pond. For decades, this remained purely theoretical, but in 1974, as a massive breakthrough occurred, two astronomers, Russell A. Hales and Joseph H. Taylor, using the Arecibo Radio Observatory in Puerto Rico, discovered a binary pulsar system. Pulsar are rapid rotating neutron stars that emit highly precise clock-like beam of radio waves. By tracking the radio emissions of these specific binary pairs over 4 years, Hussle, Taylor and their colleagues, John Bismarck and Leif Fowler, noticed something extraordinary. The star's orbital period was shrinking. They were getting closer to each other at the exact rate predicted by general theory of relativity. Because they were radiating energy always into a space as a gravitational waves, their orbit was decaying. They observed rate agreed with the Einstein equation to within a one half of 1%. This brilliant indirect proof earned Hussle Taylor the Nobel Prize in Physics in 1993, opening up a brand new window for studying the cosmos. Even with this indirect proof, actually capturing a gravitational wave directly seemed nearly impossible because this gravity acts like a weakly across the vastness of space. By the time these waves reach from Earth millions of light years away, they are thousands of billions of times smaller than when they are started. In fact, the amount of space-time wobbling that generates on Earth is less than fraction of width of a single proton, 10,000 times of smaller than atomic nucleus. To catch something that incredibly small, humanity built the most precise measuring tool ever conceived. The Laser Interferometer Gravitational Wave Observatory, or LIGO, founded by the US National Science Foundation. LIGO consists two identical widely separated detector sits in Hanford, Washington and Livingston, Louisiana, operating in unison to filter out the local vibration. LIGO utilizes as ultra-precise method is called laser interferometry. A powerful laser beam is aimed at a beam splitter which divided the light down to perpendicular, a 4 km long vacuum tube. At the end of each tube, the light bounces off exquisitely polished mirrors suspended by the multi-stage pendulum system designed to cancel out the microscopic seismic noise from the Earth. If no gravitational waves is present, the two light beams recombine at the splitter and perfectly cancel each other out, resulting in a total darkness at the light detector. However, when a gravitational waves are passed through its slightly stretched 1 4 km arm, while comparing the other, this macroscopic shift, even by a fraction of one atom width, alter the distance the laser travels. The beams fall out async, and the flicker of a light escapes the darkness, physically recording the cosmic waves. On September 14, 2015, this seemingly impossible engineering marvel worked. LIGO physically changed the undulation of space-time generated by the two colliding black holes, 1.3 billion light-years away from our Earth. It stands as one of humanity's greatest scientific milestone. Technically speaking, every single accelerating physical object produces gravitational wave, including you, me, a moving car, in fact everything. But the masses and the acceleration of objects on Earth are far too small to create repulses big enough to register, or even our most sensitive instrument. We have to look far outside our solar system to the true giants of the cosmos. Today, astrophysicists have categorized gravitational waves into four distinct classes based on their cosmic engines and the shapes of the signal they create. Let's break them down. The first class is what LIGOs hunt for the most frequently, compact binary in spiral. These are generated by the pair of incredible massive and dense objects, like the two neutron stars, two black holes, or neutron stars and black holes orbiting one another. Each distinct binary pair create a unique pattern of gravitational waves that depend heavily on the masses of each object and how far away they are, and how their orbits are orientated relative to the Earth, as they are revolved over millions of years in a phase called in spiral. They continuously radiating waves and lose orbital energy. This causes them to orbital faster and move closer together in a runway. Accelerating spin. It's a highly analogous to the spinning figure skater pulling their arm and inward to the spin faster and faster due to the conservation of momentum. Except the cosmic pair cannot stop setting off unstable into a friction of 1 second, ending in a colossal space-time, a shattering collision. The second type is continuous gravitational wave. Unlike binary systems that spiral and change rapidly, a continuous wave are expected to be produced by a single massive spinning object, like a rapidly rotating neutron star or pulsar. If that star is a perfectly spare, it's bound to produce waves. But if it has any tiny booms, structural imperfections, and asymmetries on its surface, even a microscopic mountain a few millimeters high, it will generate a steady repulses in a space-time as it spins. Because the stars spin at a highly constant and predictable rate, the resulting gravitational waves are maintained the exact same frequency and amplitude continuously. It functions much like a singer holding a single unvarying note forever. While these signals are incredibly weak, their constant, unchanging nature allows scientists to gather data over a long time to gradually pull the signal out of a background noise. Next are stochastic gravitational wave. While a massive binary events are distinct enough that their signals don't overlap and confuse our detector, astronomers presume that universe is simultaneously filled with the background hum of countless small random gravitational waves passing by the every direction at all times. This mixture creates a stochastic signal, meaning it has random pattern that cannot be predicted precisely, but must be analyzed using complex statistical methods. They are smallest and most difficult wave to isolate, but they hold ultimate price. Scientists believe a significant part of this cosmic background noise, including relics radiation left behind the Big Bang itself. Detecting these primordial repulses will allow us to look further back into the history of our universe than any light-based telescope ever could. Finally, we have burst gravitational wave. These are the wildcard of the astrophysics. Burst waves are short duration, high energy and completely unexpected signals originated from unknown unmodeled source. They come from sudden catastrophic event we either don't know enough about to mathematical predict, like a massive stars blowing itself up in a sudden supernova explosion, or things we haven't even conceived of yet. Searching for them, Record began absolutely open-minded. Lagos data analysis tool must be trained to recognize a certain pattern or spike in the data, even no scientific theory has modeled it before. Will difficult to find detecting to reveal totally revolutionary, a paradigmic shifting information about our universe. But what happened? A gravitational wave is accompanied by the actual light. That's where things get really exciting. Locating the exact source of the repulses in space-time is an incredibly difficult to using LEGO alone. But what an event amid both gravitational and light. Scientists can combine force to map the cosmos. Take a one historic event detecting by LIGO, the merger of two neutron stars, stellar courses densely packed with pure neutrons. This collision caused by an impulse explosion known as kilonova, an event more energetic than standard nova but less than supernova. The merger released a transient flash of gamma ray burst alongside gravitational wave because there was a sudden burst of light. Its expensive suite of instruments to track the precise location of kilonova within its host galaxy. This combination of seeing a light filling a space-time repulses is what scientists call multi-merger astronomy. Whether it is a study, a quiet hum of imperfect neutron star, the sudden violent burst of supernova, or cataclysmic collision of two massive black holes, a gravitational waves are completely redefining our understanding of the universe. For a century, only we are able to look at the cosmos. Now, by learning to decode the vibration of space-time itself, we are finally starting to hear it. And thank you so much for watching this video, and if you love this and deep dive into a cosmos, make sure to hit that like button and subscribe the channel and drop a comment on what cosmic mystery we should explore next.